Hello and welcome to the BinarX Student Payload Development Program Week 17, Electronic Concept Design. So this week we are going to learn how to read a data sheet, learn how to read resistor bands, the colors on resistors on the ones you've been using, and learn how to measure the values across your circuit using a multimeter. So before we start, you will need a handheld multimeter. Which I don't have with me today, but you'll see a photo of it in the next slides. And print it out, or on your computer, you'll need a copy of the TMP35 temperature sensor data sheet, just so that we're going to refer to that in our examples. And you'll need some of the physical components from your Introduction to Electronics kits. So you'll need a breadboard. You'll need a red LED, so that's on there already. Sorry, it's a bit blurry. Red LED. A 10K resistor, so that little on there if you can see it. This is actually a lot bigger of a resistor than you're going to need, but more on that later. Some pin-to-pin or male-to-male jumper cables, the little ones that are in your box that have the pins on both ends. You'll need a 9-volt battery, which is in your box. Bring it to show up. And the 9-volt battery snaps, the little connectors that connect it to the breadboard. All right, but before we start, we have some Binar Space Program updates. So our Binar 234 launched. Our first launch was scheduled for late night Saturday, August 4th, but that was postponed due to the weather. But we did have a good turnout of people come and watch, so thank you so much to those BinarX students, Pema and Jackson from Balcata Senior High School and their families, who came all the way down to watch, even though we didn't get the launch that evening. But we did launch the next day, 11:02 p.m. Perth time, so Sunday, August 5th, and you can rewatch the launch by scanning the QR code up on there in the corner, and that will take you through to NASA's YouTube video of the launch, which is really exciting, and that's a beautiful photo of the CRS NG-21 resupply mission that's supplied by SpaceX, and that is from Cape Canaveral, Florida. So there in the top right corner, you see the NG-21 mission patch, and below is the Binar 234 mission patch that we made that some of you may now have stickers up. So because we couldn't watch the launch live because it was so late at night, we held a launch celebration event at Northbridge Piazza on Tuesday, August 6th. Our team was there along with AVI, who built the S-band radio on board Binar 234, members of the WA space industry, and the media as well. So with the timing, I understand we couldn't have many of you join us, but we did have St. George's Year 10 student Zara come down with her dad and represent on behalf of the BinarX program, which was nice. The back of my head made Channel 7 news. So we were, while we were there, we were actually also able to watch the live footage being streamed down from the ISS of the Cygnus spacecraft, which was carrying Binar 234, being captured by the ISS's Canadarm2 robotic arm. So that just happened to be streaming and happening at the same time that we were in Northbridge. So we flicked over to that, and here are some photos from NASA that are just absolutely beautiful. And these are actually photos from Tuesday afternoon from space. So that is Northrop Grumman's Cygnus cargo craft. You can see its prominent symbol-shaped ultraflex solar arrays there. It's pictured awaiting its capture by the Canadarm robotic arm, commanded by Expedition 71 flight engineer Matthew Dominic of NASA. And then, so it's awaiting on the left-hand side, and then on the right, that's the moment of capture. So this is marks the 50th time that a free-flying capture has occurred from the Canadarm2. So that is pretty cool. So getting right into electronic concept design. Today we are going to try and understand how to navigate the most important parts of data sheets, which are the specification sheets that you'll need to download for your components, for resistors, LEDs, anything that you're going to use in your payload. We're going to look at commencing schematic designs, which we touched on last week, and if we have time, you can commence breadboarding your schematic diagram, but in the very least, we'll breadboard a very basic circuit with an LED and a resistor and a battery, so you can start taking some measurements of the different things you're going to need to learn about while you're designing your payload. So here is an example of a data sheet. So you have pin configuration, typical circuit, You have all kinds of things like that. So you've got on the left-hand side, you've got your pin configuration. So on a sensor or an integrated circuit that has multiple legs, or something like a temperature sensor or voltage regulator down at the bottom there, that has, you know, a voltage in, a voltage out, or a ground. You've just got to take note of what you've got, and you may even have on your data sheet 3 different packages for the same sensors. You can see what package you have or what form factor you have, and you can do that by just matching up what it looks like in the picture on the diagram compared to your chip. If it is an integrated circuit chip, notice the small dot indicating pin 1, as well as the notch showing the orientation of the integrated circuit. That's just really handy. Sometimes it'll be a notch, sometimes it'll be a flat side. Because they're so small, it just helps you keep track of which side is the correct side, which way around it goes. Otherwise, you might end up, you know, wiring it backwards, and a lot of components don't like that, and you'll end up damaging them. So if it is more similar to the TO92 or the linear voltage converter, that's similar to the one in your introduction set, take note of the shape and component and match the pins accordingly. So typical circuit, if you can find that on page 10 of your TMP35 datasheet, find and take note of the typical circuit shown in the datasheet. So that is the schematic there. And in this case, you see you've got a 0.1 microfarad capacitor on the supply voltage. And you've got to think, where would the voltage out be connected to in our circuit? So if this is a sensor, where is the voltage out going to have a think about that. And do we need to amplify or shift the signal for the microcontroller? So if we talked about that last week, if it's a very, very low signal, do we need to amplify that and make it quote unquote louder to be read by the microcontroller? Specifications. So if you go to page 3 of our data sheet, specifications, this is the most important table as you gain insights into the accuracy and the supply or the output voltages. So you also get insights into current, which can be important to know if the circuit requires more load, as ADCs or analog to digital converters work better with specific inputs. Again, don't worry about ADCs for today, just introducing the terms. Absolute maximums, page 4. That's our table shown on the right. This is really important because this is shows what the limits are in order to protect the component. So importantly, supply voltage. So there, if your circuit was high voltage, you would need to be careful of short circuits. So if it was a 7 voltage absolute maximum supply voltage, you couldn't convert a 9-volt battery to it directly. You would have to put something like that voltage regulator that I haven't asked you to use today, but that we've used in previous activities that brought it down to, say, 5 volts, assuming that was enough. The most useful one for space applications is the operating temperature range as well. So in this case, it's minus 55 degrees Celsius to plus 150 degrees Celsius, because the harsh environment of space means our component needs to survive a large range of temperatures. Again, if you're finding a component that maybe isn't in those space ranges just yet, you could still use it for your prototype. And if it's close, we can always test it, because what we've found is we've been able to push the limits of some of the components we've used beyond what the advertised absolute maximums are, but start within the range of the absolute maximums for now. So if we go to page 5, figure 6, you've got the output voltage versus the temperature. So this is a temperature sensor that we're using for our example. The red line shows the TMP35's linear voltage change depending on the temperature it is subjected to, which we use to estimate the requirements for the rest of the circuit and the potential code conversions to read this value on the microcontroller. So if we know those voltages, like what voltage range we're going to be having, any other part of the circuit is going to have to have the ability to handle that voltage. On the right, we've got page 5, figure 7, which is the accuracy error versus temperature. So it allows us to assess whether this sensor is accurate enough to answer our science question. If the sensor is highly inaccurate, we wouldn't be confident on the results we'd get on the microcontroller. So, Again, if you're not sure about interpreting these on whatever component you're selecting and you send it through to us, we can have a look at it. That's what we're here for. No, this is a lot, but but just, have a crack and send it through, and we'll support you to go from there. So breadboards, talking about breadboards now, we've worked a fair bit on breadboards, so I think a lot of you have started becoming familiar with these. Note the internal copper tracers for the orientation in which components should be placed. So those lines there on the power rails, so the bits on the top and the bottom, the copper traces, which means where that sort of copper colored line is, those are electrically connected. And then if we have a look at in what is it, row A, column 1, so sort of near the top right corner of the breadboard, you see there's a line going down there. You've got those lines are electrically connected, and then there's a gap in the middle, and then the next ones are electrically connected. So note that each one of these traces, so the internal copper traces, are considered a node in the circuit. So you see there where it's labeled as nodes, what our nodes are. So a node is the intersection of components, like where the positive side of the battery and the resistor meet. So you can see that there. With integrated circuits, like your Arduino microcontrollers, you need to ensure that the legs are not shorted on the same nodes or traces, and that's why we put them across that divider. So in the middle, there's a blank row. You can see it here. I don't have my microcontroller on it, but even though these rows are electrically connected in nodes here and here and here, there's a break in the middle of a breadboard. And so if you had to put your microcontroller, many of you already have it on there. So you'd put it so that half of the legs were going that way and on the other side with a break in the middle. Don't put it running this way, because they'll be electrically connected through there and they'll short. All right, so just a little note about resistors. Quickly, there's 10 kilo ohm resistors in the Introduction to Electronics kits. The diagrams that we've prepared for this actually only have a 1 kilo ohm resistor. So you'll see the colors of the bands are different, and I'll get to that in a second. You don't need to know this, but it's an interesting one, and it can come in handy when you don't have a multimeter on hand to measure the resistance in your resistor if you know how to read them. So on the left, the 10 kilo ohm resistors, we have a brown band, a black band, an orange band, and a gold band. And on the 1 kilo ohm resistor on the right, we have a brown band, a black band, a red band, and a gold band. So I'll go into how to read those, but you don't have to memorize this. It's just if you're interested. This is how it works. So the two resistors on the previous page were 4-band resistors. So you can see the table below, and then you go right to left or left to right on the band. So the first digit is the first band. So if we look at the arrow pointing to the first digit and we go down to brown, the first digit is a 1. We go to the second band on the resistor and it's black, which means the second digit is a 0. And the third band is the multiplier, if there are only 4 bands total. If there's 5 bands, we'll go over that in a second. So the third band is the multiplier. So you'd multiply 10 by 100 ohms, and that would give you a 1000 ohm or 1 kilo ohm resistor. With a 5-band resistor, I've actually got one here. I can't see very well, but you'll have 5 bands on it. You'll have your first band is the first digit, second band is the second digit, third band is the third digit, and then the fourth band is the multiplier. So in the case of this one here, we would have 1 being brown is the first, 1, 0, 2. So it's 102, and then times green is 100. So that would be 102 times 100 kilo ohms. So that's, what is that? Quite a lot. And the last band on both is the tolerance. So that's how much above or below the total resistance it could be. And so in this case, it's gold, so that's a 5% above and below. So if you had a 100 ohm resistor with a gold band in the end, it would be either anywhere from 95 ohms to 105 ohms. If it was, 10% sort of silver band on the end, it could be 90 ohms. And it was 100 ohm resistor, it could be either anywhere from 90 ohms to 110 ohms. So that's how you read those. But again, the resistors that are in your Bintro kits, you're probably going to find that your LEDs are a bit dim because they're 10 kilo ohm resistors. You could get away with really a 1 kilo ohm resistor, and that would be fine. If you have one on hand, just don't go too low or you'll burn out your LED. So multimeters. This is a multimeter. You may have seen one of these before. They are the ultimate debugging tool because they measure most electrical characteristics quantitatively. So they'll give you a number value for anything you need to know about your circuit. They can also validate your circuit functionality in terms of, is it all connected, and ensure electrical safety because you don't want to be passing too much voltage or current through your components. So yeah, it measures electrical properties such as voltage, current, and resistance in circuits. So I'll just quickly mention the difference between series and parallel in circuits because we're going to use these terms in the next few slides on how you are going to measure those values, but please don't worry about completely understanding these yet. We will get onto it later in the program. So in a series circuit, that top diagram, all components are connected end to end to form a single path for current flow. So basically there's just one path. In a parallel circuit, the components are connected in such a way that you actually have multiple paths for the voltage. So you have the same voltage across each component. So if there's a video in the extension on Ohm's law and calculating voltage and resistance and current. So in the series circuit, you would actually get a voltage drop across those resistors, so your voltage would go down. But in parallel, where the battery connected, you'd get the same voltage across all those resistors. So don't worry about understanding that for now, but the first thing we're going to measure on our breadboard is the multimeter. So if you take a moment and we take our breadboard, I'm actually going to pop the resistor back in there. All we need is our red LED, our breadboard, and our resistor and some wires to connect them up. And if you can connect it up exactly as you see in the diagram there, then we're going to take some measurements. And just remember, with your red LED, there's a positive side and a negative side. And the way to figure that out, if you haven't cut it down, is the shorter leg is the diode, or the negative, or sorry, the cathode, or the negative side, which is it's also a little bit flat. If you kind of run your finger, it's not perfectly round. So the negative side is the flat side. The negative side also has the shorter leg on the LED. Okay. Ooh, I'm glad I had my nails done. All right. So check our voltage. We're going to show, we want to, checking voltage will show the potential difference between 2 points in the circuit. So it needs to be measured in parallel with the circuit. So you're going to see if we've got a 9-volt battery and you connect your multimeter and you turn it, just note where the little dial on the multimeter is turned, which is the V with the line and the dotted line under it. That's for DC, measuring DC voltage. So we've got our red probe on the positive side of the LED, and we've got our negative probe, or the black one, on the negative side, or the flat side of the LED with the shorter leg. You should also note the way you should have your leads plugged into your multimeter. Just see in the diagram of the multimeter there, make sure they're plugged into the ones that have the red dot and the black dot on them. So in real life, if you're sitting there with your multimeter and your tiny breadboard, you may find it's very difficult to get your probes down there because they're not that small and they don't really fit into the breadboard very well. So a good trick that I was taught was taking these little jumper leads, and we're going to just connect them in. So where you see, and I've got a red one and a black one just to make it easy. So to represent the black probe, I'm going to put in my jumper lead exactly where it is on that diagram. So you can see I've put it in. Hopefully you can see that. I've put it in there. And then I'm going to take the red one and I'm going to put it in where the red probe is showing on that circuit. So now I have 2 of these sticking out. And what you can do is, if you're working in pairs or groups, have one person hold, because it's hard to do both. Hold the little pin still and turn on your multimeter, and then touch the multimeters, the red and the black, to the end pin on the red and the black. leads there, and then you'll get your reading. Great. So I'm going to go ahead and light this up right now, and what you'll see, you'll also connect your battery snaps. So these ones here, you'll connect those to your power rail. And just make sure, like you see in there, if you don't have a power rail, you should have a power rail on your breadboard. If you don't, you can just connect it directly to the same node. You'll be fine. So I've got my battery snaps in there now, connected on the power rail. And just as a matter of safety, before you connect your power, make sure you have checked all your connections, that everything's sitting, that nothing is touched, no metal legs are touching each other and shorting out. So I'm going to go ahead and turn on my circuit by plugging in the battery. So I plugged in the battery there. And my LED is shining brightly. Now, the resistor I have here is a 1K resistor. The resistor you have is probably a 10K resistor, which is higher. So I'm just going to quickly pause and switch out the resistors so that you can see that there's actually quite a difference. So my resistor is a little bit different from the one you'll have. This is one of the 5-band resistors, but that's a roughly a 10 kilo ohm resistor. So I'm just going to pop it in the same way as the other one was, just like that. That's in there nicely. Make sure nothing is shorting out. Make sure everything's nice. Oh, my battery snaps have fallen off. You might find that the battery snap wires are a bit short, but that's all right. You can always strip back some of the insulation and make them a little bit more robust. And now I've plugged in my LED, and I don't know if you can even see that. It's very dim as compared to what it was previously, but that's okay. I mean, it's still running, but sometimes you won't get it on, get the LED turning on at all. And if your circuit's otherwise correct, you may have too much resistance and your LED isn't getting enough power. Anyhow, so yes, go ahead and measure your voltage. And so if you've got a 9-volt battery, you can measure your battery voltage by putting the probes on both terminals, making sure you connect the black to the negative and the red to the positive side of your battery. See what that voltage is, and then compare that to what you're measuring on your circuit. All right, so the next thing we're going to check is the current. So checking current determines how much charge is flowing through the circuit. It must be measured in series with the circuit. So you can note on the breadboard where the black probe and the red probe are. But before we measure the current in our circuit, have a look at the diagram of the multimeter on the right-hand side. Where the yellow arrow is pointing, the A with the straight line and the dashed line, that's what you're going to have to turn your dial to. And move the red probe over from the red port that says V in ohms over to the other side as shown, and it will say A. So then if you measure, you plug your battery back in after you've checked all your connections, make sure they're still secure, and then measure as shown in the diagram, again using the jumper leads if you need to make it a bit easier to measure your using your multimeter. So having these plugged in with the little metal bits, then see how much current is flowing through your circuit. Next, we'll measure resistance. Resistance is the amount of opposition to the flow of charge. It's useful for checking the value of the component and is done in parallel to the component. So you can see we're checking the resistor's resistance value. So switch your red probe back over to the other side as shown in the multimeter image on the right-hand side, and turn the dial to the spot shown by the yellow arrow, which is the ohm symbol, which is the symbol for resistance, and see what you get. So the value that you get there should be the value of the resistor. So you can check that by also going back and seeing if you can double check that with the band colors using the chart that we looked at before. The last thing we're going to learn to check today is the continuity check with the multimeter. Continuity is checking for, does this connect to this? It's useful for checking if unintentional or intentional connections are made. So you can actually use this sort of check to check your soldering. So if you're soldering header pins onto your Arduinos from your kits, or just doing any soldering in general, and you know that two parts aren't supposed to be connected, you can check if they've been connected or bridged using this function. So again, with your probe in black one doesn't actually ever move, but the probe and the multimeter on the red one on the right hand side, as shown in the diagram on the right of your screen. Turn your dial to, now some multimeters are different to get the tone, but if it's looking like this, turn the dial to the spot shown by the yellow arrow. It looks like a little sort of beep sound or noise sound. And if you connect your the black probe to the negative side of the LED and the red probe to the positive side, or where the power is connecting to the battery, you should hear a beep. So you can also test easily to see if you've got it set right, is just touch the two multimeter probes together, and if it's on the right setting, it'll beep because they're continuous with each other. Okay, so if you're having trouble, some good questions to check, or a little checklist to go down, is are the components oriented in the correct direction? So on the breadboards, we remember the electrical connections run that way, so those nodes are all electrically connected. If you have a negative and a positive side, like on your LED, you've got to make sure that those are on separate nodes, like that. So going across the breadboard, not down. Are your passive components the expected values? So are your resistors the values that you think they should be, or that you understand them to be? So if you know you have a 10K resistor and you measure it and you're not getting that resistance, there might be something showing up on your multimeter. There might be something wrong with your circuit, the way it's wired up. Does each node have the correct connections? Does it have voltage in? Does it have voltage out? Positive, negative. Does it have everything it needs? Is the circuit complete? And check and see how much voltage you're supplying to your circuit. So just be mindful. The 9-volt battery is all right for most things, but there are some components that only take 5 volts or 3V3. You need to make sure you don't feed them more voltage than they can handle. On the CubeSats, you'll be operating, your payloads will have sort of 5 volts going into the microboards, and then 3.3 volts coming out onto your components. So you probably will want to sort of work on things that are in that neighborhood as well. So just a reminder, a node on a breadboard is the line where multiple connections are made. It's normally distinguished with the number side. So if it's node, you probably can't read this, but if you have a look at your own breadboards, you'll see A, B, C, D, E, F, G, H, I, J, but then you'll see 1, 2, 3, 4, 5, 6, 7, and so on. Those number columns are normally the nodes, so the ones that are electrically connected. In terms of safety, I've mentioned this a few times through the presentation already. Do not power up your circuit, so do not connect your battery until you've triple checked your connections, because you could damage your components, or just actually make sure you've got everything the right way around as well. Once powered, do not touch any components as they may be hot. Remember, we discussed in previous weeks, you can have low voltage but still reasonably high current, and that high current can generate heat, and you could burn yourself. So please be careful. If you see smoke, disconnect the circuit immediately, and do not leave connected circuits unattended either for any length of time. So yes. So that's it for this week in BinarX. Thanks for listening. I know it was a bit of a long one, but next week we are doing a payload preliminary design research activity. So you're going to research your sensors and components. I know some of you have already started this. You're starting to send through parts lists, which is awesome. Depending on your team's progress, you can continue to work on your requirements. If you haven't quite got there yet, don't stress. Your block diagrams, and then from this week you can work on your schematics and your breadboarding. Please send through your questions and progress to binarx@curtin.edu.au. We are here to support you, and actually we're just really curious to see what you're all getting up to. So even if it's just some photos of the the sketches and the things that you've been doing, or just like a one-liner with your key headline requirement, we'd love to hear it. Thank you so much. And oh, one last thing, I'll see you all before then, and I'll mention it again next week, but we'll be deploying Binar 2, 3, and 4 from the International Space Station in a few weeks' time, so that'll be something really exciting to watch. So that photo that you keep seeing in week-over-week presentation, that was just after deployment of Binar 1, so we're going to have some fresh ones of that, and a couple of years' time, it'll be you guys with your payloads and tech on board those CubeSats. So yeah, keep going, and thanks so much. Bye now.